We are in section 4.3 on page 12. In summary, if f prime of x is increasing on your interval from a to b, then f of x is concave up on that interval. And if the derivative is decreasing on a to b, then f of x is concave down on that interval. In other words, inflection points occur at the graph of the derivative's local extrema, the mins and the maxes. There's an example next that says, given the graph below of f double prime, so second derivative, find inflection points in intervals of concavity. So we are given a second derivative graph. So your inflection points are where that second derivative would equal 0, which are going to be your x-intercepts. And then to figure out where your graph is concave up, that would be where the second derivative is greater than 0, so above the x-axis. And to find out where your graph is concave down, your function is concave down, then that would be below the x-axis. So your inflection points would occur at your x-intercepts, which is at 0 and at 2. So inflection points are going to occur at 0, comma, f of 0, and 2, comma, f of 2. And then where is our graph concave up? And I'll just write CU for concave up and CD for concave down. And looking at our graph, it is above the x-axis is where it's going to be concave up. And that happens from negative infinity to 0 and from 2 to infinity. And concave down is where it's below, which is going to be between 0 and 2. And again, this is because your second derivative is less than 0, where it's concave down, and above because that's where your second derivative is greater than 0. So in summary, the second derivative is positive, then the graph is concave up. If the second derivative is negative, then your function is concave down. Inflection points occur at the graph's x-intercept on the second derivative, where the graph of the second derivative changes signs. So there's some different pictures on here that you guys can take some time to look at. And we're going to be using that on the next example, which says, sketch a possible graph of a function f that satisfies the following conditions. And again, students struggle with this anytime that it's asking you guys to graph given information. So the first thing we're going to do is kind of break this into our intervals and kind of look at what we're given. So I'm going to make a number line, and we'll use that to help us graph. And I noticed that most of the values that we have where it's changing sign is at 1, at -2, at +2, and those are the values that I'm noticing. So I'm going to go ahead and put those numbers on a number line. And then I also noticed that it's talking about the first derivative and the second derivative. And just to kind of break this up, because there's a lot going on, I'll just make some little lines in here to kind of separate my intervals and keep everything clean. Okay, so the first thing says that the derivative is greater than 0 from negative infinity to +1. So if your first derivative is greater than 0, that means that you have a positive slope. That means that your function is increasing. All of these little intervals from negative infinity until +1 are increasing. And then we have f prime is less than 0 from 1 to infinity. So that means our slope is negative, so we're going to be decreasing in all these intervals. Okay, so likewise, the second derivative is greater than 0, which means we have a concave up function from negative infinity to negative 2. So this would be concave up. And from 2 to infinity, so concave up also over here. And then we have the second derivative is less than 0 from negative 2 to positive 2. So that means that that's going to be concave down. And then the last thing tells us what's going on with those ends of the graph as x approaches negative infinity and positive infinity. That's what we saw before. But I want you guys to notice that these three are all the same. So we need to graph this. So go ahead and make a coordinate plane. I'm going to go ahead and put -2, -1, 0, 1, and 2 on my graph. And looking at the first thing that we have is when the second derivative changes signs, we have inflection points. So you have an inflection point at -2 and also at +2. And then we have, let's see, on the first derivative, it changes at +1 from being above greater than 0, so it's increasing. So it goes from being increasing to decreasing, which means we're going to have a max, a local max at 1. So nice things to keep in mind. So going in and graphing our function, the first interval here from negative infinity to -2 is concave up and increasing. So kind of drawing that in. And then it's going to switch, and from -2 all the way to 1, it is going to be increasing and concave down. So we can switch that. And this again goes all the way on to 1. And make sure you realize that 1 is going to be your maximum value that you have. It's your max. And then it's going to switch from being concave down to increasing. So concave down and increasing looks something like this. Concave up and increasing looks something like this. And then it's going to switch to being concave down and decreasing. So concave down and decreasing, that's using those pictures up above. And that is going to happen just from 1 to 2. So there's your max. And then it's going to switch again, and it's going to be concave up and increasing and decreasing. So concave up and decreasing. And looking at the ends, it says that as it goes off to positive infinity, your graph is just going downwards. And the other one says that as it goes off to negative infinity, we actually have a horizontal asymptote at -3. So we'll go ahead and put that in 1, 2, and 3. -3. So if you want to put little dashes there, you can, but your graph is approaching that value. Again, the graphs can all be done differently and still be correct. So we get more into the graphing in section 4.5, so the next unit. So at the bottom it says, we have a method for finding the absolute maximum, absolute minimum on a closed interval from A to B. You substitute in your critical values and your endpoints into the function and find the biggest and the smallest output, so y values. The next thing that we have is the local maximums and minimums only occur at critical points, which is where your first derivative is undefined or where your first derivative is equal to 0. At each critical value f of x, it's possible to have a local minimum, a local maximum, or neither. We have two tests for determining whether critical values are local maximums, local minimums, or neither. This is the first and the second derivative test. This section is big and it has a lot of material in it, and it's good to kind of make an outline of everything that's going on and keep everything clean with this. It's also useful for the next unit because we go into graphing, which is going to be using all of this information. So if you don't learn it well, it's not going to just hurt you this time, but it will also hurt you in the next unit.